In this video, we're going to do example 5.2.4, where we are asked to evaluate the double integral over d of 2x plus 2y dA in both orders of integration, where d is this region given down below. So let's start with a type 1 order. And a type 1 order, we need bounds that are left, right. We need x bounds that are numbers, and so 0 is less than or equal to x is less than or equal to 1. And we need bounds in top and bottom that are functions. And so the bottom function is the function y is equal to 0. And the top function, if we have a straight line going through the origin and the point 1, 2, then that is y is equal to 2x. And so we have 0 is less than or equal to y is less than or equal to 2x. You can think of this as the y values traveling from 0 up to 2x. So that gives us the iterated integral that we need for this region D as a type 1 region. So we have the integral from 0 to 1 of the integral from 0 to 2x of 2x plus 2y, and the order that we've chosen is dy dx. And now this is an iterated integral, just like we were doing with rectangular regions. So that means we calculate the inner integral first with respect to y, pretending that x is a constant. And so we are going to have, so the integral from 0 to 1, we need an antiderivative inside that we're going to evaluate from 0 to 2x, and then we'll do the integral with respect to x of the result. So we need an antiderivative here with respect to y, and so that's going to give us 2xy plus y squared. Now we run this from 0 to 2x, so we plug in 2x for the y value, and then we plug in 0, so we're going to end up by getting, so the integral from 0 to 1 of 2x times 2x plus 2x all squared minus 0 dx, which is the integral from 0 to 1 of, and what are we getting here, 4x squared plus 4x squared dx, or the integral from 0 to 1 of 8x squared, 8x squared dx, which is 8/3 x cubed from 0 to 1, or 8/3. So now we're going to rewrite that region D as a type 2 region, do the integral as a type 2 double integral, and hopefully get the same answer. So let's try it. As a type 2 region, well, now we need our bounds to be constants in the y. So 0 to 2. So 0 is less than or equal to y is less than or equal to 2. And we need our boundaries to be in terms of x function. So this line here, right, if I rewrite that and solve for x, I'm going to get x is 1/2 y. And this over here, this vertical line is the line x is equal to 1. And so you're imagining that x travels from one to the other. And so 1/2 y is less than or equal to x is less than or equal to 1. Those give us the bounds of the iterated integral in the type 2 order. And so we're having from 0 to 2, the integral from 1/2 y to 1 of the same function, 2x plus 2y, but now the order of integration has changed, dx dy. So we're running the inside integral in terms of x, so we're looking for an antiderivative that we will then use the FTC on from 1/2 to 1, and then the result will be integrated with respect to y. And so this integral here, we need an antiderivative with respect to x. We're going to get x squared plus 2xy, we need to run this from 1 to y, so the integral from 0 to 2 of, so 1 squared plus 2y minus, and then I plug in 1/2 y, so I'm going to get 1/4 y squared plus and 1/4, 1/2, so what am I doing here? 1/2 times 2, they cancel. Y goes in for x, so y plus y squared. And that is going to be dy. Let's clean that up a little bit. So the integral from 0 to 2 of 1 plus 2y. And what do we have here? 1/4, 5/4 minus 5/4 y squared dy. So that is, using the FTC, y plus y squared minus 5/12 y cubed from 0 to 2. And so that is going to give us 2 plus 4 minus 5/12 times 8. So let's clean this up a little bit. So 6 minus, if we divide by 4 on both of these, we'll get 2 and thirds. So 6 minus 10 thirds, which is 18 thirds minus 10 thirds, which gives us 8 thirds, which thankfully is the same answer that we got in the other order. So some regions, as we saw before, some regions can be easily set up as both type 1 and type 2. Some integrals are easy both ways. Obviously, you see, I think that the first one was algebraically a little easier, but this one wasn't tough. We're going to see in the next videos some examples where switching the order is essential to being able to evaluate the integral.